So welcome to the Winds and Currents webinar. Today we have Jin-Song from the Max Planck Institute, who's going to talk about the role of wind work for the ocean circulation. I'll let you take it away.
Thanks. Yeah, it's my pleasure to be here to talk about my work together with Fine Rachel. And it's, as the title says, it's a wind work, the role of wind work for the ocean circulation. So I have, oh, sorry, I can move forward. So this is a simple idea. And this is about, we have this overturning circulation in red, indicating the overturning in the ocean, and we need mechanical to sustain that circulation. And it's thought that we have the tides from below and the wind from above, and therefore there has been many papers on that, the wind power input to the ocean. And it starts with these dark numbers, early estimates, roughly about 0.5 terawatt input. And then later there's these red ones, they are indicating that if you use different wind products, using, for instance, instead of 6 hourly data, you get higher input. So everything is sensitive. And then are the two recent ones, and they give us somewhat lower numbers. And so there are quite some uncertainty, and in particular, the early estimates, they are based on lab slide models. So this basically just a momentum equation, and then in that equation you have the Coriolis force and the wind stress and some linear drag. So in this type of model, if you have the wind forcing, you will have directly the response in the ocean current. And so this will behave totally different from what I'm going to show. And this is that so the input, power input, depends on the resolution of the wind, in particular temporal resolution, and also depends on how the wind stress is formulated. If you use it as formula based on Bike formula to take into account the relative velocity rather than just using reanalysis product or wind stress product, that give you different results. The wind on the top actually is not really what we are interested in. We're interested in what is really can be considered as wave source that go into the ocean interior and become available for the interior mixing. And so our concern is more the near inertial wave energy flux at the mixed layer bottom. And they are actually also is a topic has been considered since quite some time. Originally, that was proposed by Gill that if you have the wind at the surface, you will generate some vertical flows in the mixed layer, and that will produce Ekman type vertical velocity across the bottom of the mixed layer, and that will excite waves. So these are really the near inertial waves rather than near inertial oscillations in this surface layer, which maybe just oscillate but not really propagate as a wave. But those will propagate as a wave, and those are really interested in our context. And also there's another aspect is these tropical cyclones. And in the early estimates, they have not been really considered, and in most of them, they are not really considered. And but there are quite some works, studies on the role of tropical cyclones. In particular, it is thought that tropical cyclones the most efficient wave maker. They can generate really strong inertial waves. And so we thought that given all this broad picture and very different estimates, is maybe a time to reconsider that, re-examine this whole thing using frontier simulation. This is a coupled 5 kilometer coupled atmosphere ocean simulation to see what can we learn from these simulation. What is the story here? And in particular, we can quantify the role of tropical cyclones and also the near inertial wave energy flux from the radiate away from the mixed layer bottom to reconsider this. So that's just the idea why we're doing that, redoing that. And so what I will give you a brief introduction to this simulation and how we analyze the result, and then present the results with respect to the structure, spatial distribution, and some case studies, and also some spectral analysis results. And then finally give some discussions and summary. The model we're using is the 5 kilometer coupled so-called ICON simulation. ICON stands for icosahedral. N stands for non-hydrostatic, but this is only for the atmosphere. So we have ICON is triangular grid, has triangular grids, the atmosphere and the ocean, but the atmosphere is non-hydrostatic, the ocean is primitive. And we have 5 kilometer horizontal resolution in both atmosphere and ocean. This is 1 year simulation. Actually, it's come out of a series of attempts to make this kilometer scale coupled simulation running. And the atmosphere and ocean are coupled every 50 minutes. So we will think, okay, the coupling frequency is much higher. Maybe we can generate more input, and it will turn out that is not the case. And the wind stress is formulated as a function based on bulk formula. So we take the relative velocity between atmosphere and ocean into account. And in the ocean, we have very high vertical resolution, not only horizontal. So apart from the first layer, we have the layer thickness about 3 meters in the upper 140 meters. So it's we hope that have a good representation of mixed layer and also wave processes in the upper ocean. And we have analyzed is about 40 days. One is from the second half of August to September. So that will be our borrowed summer period. We call it September period. And then the others from the second half of January to February, another 40 days, about 39 days. And for that, we have only 3 hourly data, but lots of results are based on the hourly data from the borrowed summer period. Okay, let's give you some impressions about how this coupled model produce what type of wind is producing. I'm showing you here standard deviation of hourly zonal wind stress for this full 40 days period. The left panel for the February and then the right for September, and top for the ERA 5 data, and the lower panel is what we simulate. So you see that the cross feature that you have stronger variability of wind stress during in the winter hemisphere, that's clearly reproduced, and we have roundabout also similar magnitude of variability. One thing what is quite somewhat different is if you look at the lower right panel where ICON simulates quite some tropical cyclones, you see this high variability track. And in the ERA 5, in that particular 40 days, we also have some 2 or 3 of them, but not as many as in the ICON. We cannot tell whether that is coincidence or overestimation. We just take as it is. That's what we have. And then what we are going to consider is first of all, the input at the surface, near inertial motion input. And this is calculated as the covariance between the wind stress anomaly and velocity, surface velocity anomaly. That anomaly is band pass filtered variability in this near inertial range. And then we also consider the near inertial wave energy at the bottom of the mixed layer. This is a bit complicated quantity, and this is also a core variance. And the prime here, the W prime, this is the vertical velocity anomaly, and the P prime is the pressure anomaly, and both are within the sub-inertial frequency range, so above the local near inertial frequency. We consider that because the wave motion, we have also higher harmonics, and also the wave tends to can propagate equatorward. So we are not considering just truly the near inertial range, but the entire super inertial frequency range. And then this energy flux is, we consider only that at the bottom of the mixed layer, and the mixed layer is moving. We have that diagnosed for each time, but then we take the maximum mixed layer in each considered period, 40-day period, so that we are sure that what we diagnose are really inside the ocean interior, outside the mixed layer. Okay, and then we are doing also consider some spectrum. We consider the co-spectrum between wind stress and surface current. And these are just simply the real part of the cross spectrum between these the quantity, surface current, and wind stress, and also the vertical velocity and pressure. And we also consider the power spectrum of the velocity. And here, the emphasis is really on the waves. We think the vertical velocity will reflect lots of wave features. And just to remind you that the co-spectrum is it can be as a co-spectrum decompose the total core variance between two variables, and the co-spectrum is defined as positive when the flux is when showing the downward flux. Then you have positive co-spectrum. Okay, so coming to the result, the first one shows the input distribution of power input during the September period. And the global integral, as you see, is 0.28 terawatt. So it's at the low of the study. And basically, you have similar picture as you had before from other estimates. You have higher, stronger input in the winter hemisphere, in the at winter mid-high latitudes ocean. And but here in this simulation, you also have this strong input along the tropical cyclones tracks. This is something what we haven't seen so far from the other analysis. And then if you look at the flux, now this is a flux at the bottom of the mixed layer, and we have very strong positive flux, downward flux at the flux of super inertial during at super inertial range, and this flux is quite strong, and we can maybe just look into one of these small areas where tropical cyclone passing through during that period. And showing you here is in the inset is the contour is the input at the top, at the surface, and then the shadings are the flux beneath the mixed layer. And you see that it can reach quite high number, something like 20 milliwatts per square meter. And if you consider strong, that's what I said. And if you consider the ratio of the flux relative to input, you get this picture. What you see is that in the mid latitude, it's basically positive, and in the range something like between yeah, say 0.3, 0.5 or something. And but in the low latitude, it's huge number. Huge means larger than 1. And this is the areas where the input, the wind input is small, but you have lots of wave fluxes, and that makes this flux, this ratio much larger. And you also have alternating magnitude. And this is just showing you what in the same region where we have this one size, this ratio is about something like 0.5. And then, but the outside, in particular, if you remember the figure I showed before here, that you have these lines of basically no input. And therefore, if you do calculate the flux, that give you huge values here. But you do have the calculate the ratio. You do have the flux, but small input that give you large values. And in the second part of the result, I would like to show some case studies. The idea here is to show you how the 5-kilometer ocean react to the 5-kilometer atmosphere. And the reaction is quite different depending on how strong the wind forcing is. So we'll have situation first in the during the summertime in the subtropical region, where you have one case with cyclone, tropical cyclone, in one case without tropical cyclone. The big difference certainly is the magnitude of the wind stress. That can be about 10 Pascal when you have tropical cyclone, and below 0.1 Pascal if you don't. So the situation is very different in these two cases. And then we consider also the case where during normal wintertime condition, that's then in the southern hemisphere, where the typical wind stress magnitude is about 0.5 Pascal. So this is the case in the subtropics where we have a tropical cyclone. In the top panel, I show the in arrow the wind stress vector, and in contour the magnitude. So you have a tropical cyclone which increases with wind stress, which increases towards the eye and then decreases towards the eye. So and this is the two left and right panel. These are 6 hours apart, and so we see that this tropical cyclone is moving northwestward, and within 6 hours about 100 kilometers. And what happens in the ocean is showing below. What I'm showing here is the current, surface current in the as arrows, and then in color is the vertical velocity at the bottom of the mixed layer. And then I have to identify the core region of the tropical cyclone. I show the isolines of the wind stress we saw in the top panel. And so what we can see is that the surface current is actually stronger on the side north and east of the tropical cyclone, on the side where the cyclone moves. The rotation of the cyclone is in the same direction as the movement of the cyclone. On the other side is then weaker. The current is weaker. And also we have this strong downward velocity just in front of the core of the tropical cyclone, and then upward on the other side. So it looks like that in the ocean, that in the surface ocean, that everything is quite strongly detected by the winds, by the cyclonic winds. But if we have a weak weather condition, so weak weather disturbances, like in this case, that the winds much lower. That's the typical summer condition in the subtropical region. And again, this is two snapshots about 8 hours apart. And you see that there you have some wind stress which are quite weak. And in the ocean, what you see is that you have the eddies, one eddy on the left of the panel, and this is there during this in 8 hours. It doesn't change very much. So it looks like that the surface ocean does not really show direct response to the small wind stress related to weak weather disturbances. And similarly, here is in mid-latitude, here the wind stress somewhat stronger, is up to 0.5 Pascal. And here we have kind of storm coming, and 8 hours later, what passing through the region we are considering here. And in the ocean, you have this meandering situation, and it looks like that this situation is not really affected by the surface wind. So similarly, in this case, this is a quite standard case where you have the westerlies in the during the in the winter hemisphere, and in the ocean you have here the overall there's a tendency for the flow to move westward, but there's a lot of structure there, and this structure basically stays the same during these at these 2 time steps. So again, the situation is that we have, so in this case, the surface currents tends to move westward, but there are strong meandering features which seems to be not directly related to the wind stress. So that's the case study we have. And then I would like to move on to the spectral analysis. Here I show you the spectrum, the co-spectrum between wind stress and surface current, and between the vertical velocity and pressure at the bottom of the mixed layer, and then the power spectrum of the vertical velocity only. And these are spectrum averaged over zonal band, which is quite thin, about 0.2 degrees, and they're about 5 degrees long. Zonal bands, and the red is a band at about 24 degrees north, and that's this place where we have a tropical cyclone, and the equatorward of that, these are 2 bands where we don't have tropical cyclones. And then we have the dashed lines are the local Coriolis frequency, and the dotted lines are 2 times of that, the color corresponding to the zonal band. So what you see is that under the tropical cyclone, you have really much stronger input compared to south of that. And you have then also strong wave flux and strong energy in the vertical velocity. And this, from the vertical velocity, you see that the maximum is at the latitude 24 degrees north, where you have the tropical cyclones. And if you move equatorwards in the blue and green lines, you have the maximum at the same location, and also at the higher harmonics. This indicates that these tropical cyclones generate waves, and these waves propagate equatorwards and keep that frequency. So you still see them at lower frequencies. Let me move on to show you another 2 picture of the power spectrum of the vertical velocity at the bottom of mixed layer. This is during winter season. It's a northern hemisphere. So the left are at lower latitude, and right at higher latitude, again at different latitudes. And what you see first is at higher latitude, the peaks. They peak at the local Coriolis frequency, but the widths of the peak are much narrower compared to those at the lower latitude. For the green line at 16 degrees north, you have a maximum, small maximum at the local inertial frequency, but then you have a broad maximum at higher frequency. So this indicates that we have the waves excited at high latitude, and those waves moves downward towards the equator. I think I need to move a bit faster to discuss one. One thing is that we got wave input or energy power input, which is quite low, and how to understand that. And we think that has something to do with this eddy killing process. So if the wind stress is formulated as depending on the relative velocity between air and water, then this wind stress arising from large-scale circulation can act to damp an eddy, and this is described in this figure. So you have the large-scale flow indicated by big bright arrow, and then you have this eddy by the circle indicated by this circle. So in the upper part, where the eddy flows in the opposite direction of the large-scale atmospheric flow, the atmospheric flow damps the eddy, and in the lower part it accelerates, but the relative velocity in the upper part is larger, so this damping is stronger. So if you average over the spatially, then you have a damping, and this things seems to work, has been shown by several other authors, and we think that in our case we don't have this quite regular thing in as indicated by this sketch, but we have this quite random assignment between wind stress and surface current, as I show in the case study, that we have both that randomly that happens that the wind stress is in the direction of the current and sometimes also opposite. So if you integrate in time, and we think that exactly the similar mechanism will take place, so that we have stronger damping when average over time than acceleration. So there will be therefore the input could make the input smaller, and this happens in particular if we have weak weather disturbances, then the wind stress is also weak, and in that case we will have this type of situation. And then I think I skip that part. And one issue which we think is important is also the we want to, at the end, we want to parameterize the wind-induced wave source. This is this flux at the bottom of the mix. And to return to my idealized picture at the beginning, what we want is we want to have to describe the mixing in the interior. And there's actually a parameterization developed by Olbers and Eden, and this is a so-called ED mix. This is parameterization that involves the wave propagation, dissipation, and all those process, but it needs as wave energy input at the bottom and at the top. So if we want to have that in the model, and this what we're trying to do now is we need to have the right input wave source at the top. And the thing is that this wave energy source at the bottom of the mix layer, that is not the same as what you put in at the surface. And also this wave source is also difficult to describe or to quantify. And the way out here could be that we parameterize this flux in terms of the input at the surface, and then make use of the property of this ratio, what I showed before, the flux over input ratio. And we saw the global maps, which is quite messy, but if you integrate it zonally, this is the result what we get. And it shows quite clearly we have this ratio, which is always positive, and then it has clear feature to try to increase with decreasing latitude towards, so the ratio increases towards the equator in both seasons. And so this has something to do with the fact that we generate waves at the high latitude, and those waves moves propagates equatorwards, and therefore you have stronger flux towards the equator. In that sense, that we can use this ratio and then infer the flux at the bottom of mixed sphere in terms of this ratio and in terms of the input at the surface. And that can be then implemented into the parameterization schemes such as EDMix. Yeah, that's about what I want to say. So coming back to what we found is that the wind-induced wave energy source is actually pretty weak. It's smaller than 0.1 terawatts. And this smaller value comes because this damping effect and eddy killing effect that results from the random assignment between wind stress we got under weak weather condition, weather disturbance, and with a strong internally generated current. So the currents reflects we saw this meandering feature and eddying feature, which are induced by the internal dynamics, which has nothing to do with wind stress. And therefore we have quite often these situations that the wind stress and surface current are not aligned in the way as you would have if you have a slab ocean. And that give you this weight input. So that in this model that we have quite strong tropical cyclones, so that the flux to input ratio is quite high. It's about 30%, and in the previous estimate it's something like 11 to 17%. So it's quite strong due to the strong cyclones. But nevertheless, because it's this the overall is quite give us a quite small number. And then from we show that this flux to input ratio, that is something which is latitudinal dependent. Actually, it depends also on the mixed layer depth. And this useful information that can be used to parameterize the energy source at the surface, wave energy source at the surface. And I try to show also that we find quite a few interesting inertial wave features that can be simulated by the Icon Ocean model. That includes the strong generation of near inertial waves under tropical cyclones, and not only as an inertial frequency, but also as higher harmonics. And we see the equatorial propagation, and that leads to broadening of the wave spectral maximum at the lower frequency. Actually, we see also poleward propagation of higher harmonics that I didn't really come to that. So with that, I want to thank you for your attention.
Thank you so much for this really interesting talk. And we can open the floor for questions. So maybe while people are thinking about questions, I'll ask one to get started. Yeah. I'm just curious, you show that tropical storms are a really big force in this model. What fraction of the overall energy input is coming out of extreme events like tropical storms?
Oh, that's, I guess that's the standard case related with warm SST, and but I didn't really look into that. I think there are one or two papers which really look into details about how realistic the tropical cyclones are simulated by this model. and they do find some features like the cold wake, but I couldn't tell you more because I'm not really I didn't do it myself, and and there's tendency for that model that at least for these 1 year simulations that we got quite a lot tropical cyclones, but we don't know whether that is the problem of the model or that's just particular situation of that year. Yeah.
Interesting.
I think I just stop sharing.
So there's a question in the chat from Shikar Rai. Do you want to go ahead and ask that, Shikar, or do you want me to read it?
Let me see. I didn't.
Okay, I'll read it out then.
Yeah.
He says, thank you for such a nice presentation. He has a basic question. Is the global ocean circulation being maintained largely by just the near inertial wave frequency flux to the interior? How much does the input to large scale potential energy contribute? How much does the energy input by the shear contribute to maintain the circulation?
Oh, that's a complicated question. Actually, the idea is also not that the mechanical energy is not just from the winds, but also from the tides. And the thing here is not too much about how that go into large scale potential energy, but the question is really about waves. We think that the mechanical energy that can be used for mixing that comes from waves. When the waves through wave-wave interaction from large scale wave, low modes into high modes, and then they start to break. And that's the situation where they can become efficient in providing mixing. And this is also the idea of EDMX to describe this process. This is purely wave process, and therefore we are keen to really just identify the sources of the wave energy, so that when the waves propagate away and interact with others, so they can break and then provide energy for mixing. I think that's what all I can say.
Thanks. Rick Danielson has his hand up. Rick, do you want to go ahead?
Yeah, hi, Jin-Song. Great presentation. I love the model setup, and I'm just wondering if you can comment a little bit on some earlier ideas about propagating near inertial wave energy into the interior, preferentially in the presence of cyclonic eddies versus anticyclonic eddies in the ocean. How, I mean, when the signal's small like this, is it possible to distinguish that sort of vertical propagation into the interior as a function of the presence of ocean eddies somehow, or is it?
Yeah, there are quite some studies, yeah, in that direction.
I'm thinking, yeah, Greatbatch and Zai have been publishing about that for a while. I was just wondering if you could reconcile with them.
Yeah, we didn't separate the cyclonic, anticyclonic, so I cannot say.
Okay, fair enough.
So I cannot say, but yeah, but the thing, the idea what actually in this Orbis and Oil paper was not necessarily cyclonic or anticyclonic. It's really just about that you have the vertical flow, Ekman type of pumping velocity that excite waves. And not so much about how the waves will be trapped inside anticyclone or things like that. It's really waves rather than how the waves will survive or not survive in the eddies or not. So it's somewhat different topic, and we didn't look. Yeah.
Fair enough. So there'd be no signal. I mean, if you wanted to, if you wanted to reach those topics, would you have to look over the time scale, longer time scale than you're I mean, in terms of, not just a month,
Yeah,
maybe.
I
But
guess so. Yeah, I guess so, because eddies will be there for quite some time. I don't
Right.
know, weeks or months or whatever.
Right.
And yeah.
Okay, thanks.
Shen Elipot has his hand up.
Hello, thank you very much
Hi.
for your presentation. So at the beginning, I think you mentioned that you bandpass filtered velocity and wind stress between 0.8 F and 1.2 F. I didn't really understand if that had any influence on the flux at the bottom of the mix layer. I mean, do you also band limit the flux in those frequencies, or do you take the entire co-spectrum of W and P?
Oh no, if I do spectrum, I don't filter. But if I calculate the flux or the input to near inertial motions, I use the filtered data. But if I look at the spectrum, I take the full velocity of wind stress to the cross spectrum. And
does it matter a
I
lot if you
understand.
do? Yeah, does it matter a lot if you change the limit of your bandpass? Like,
yeah, that we change a little bit. That will give your number somewhat differently, but we are still in the low range of the previous numbers. So that does not change the whole picture, but that will change definitely some, the exact number you get for the power input and the,
Thank you.
If I can ask another question, you have this model with amazing resolution and amazing numbers of vertical levels. How much do you need the 5 kilometer resolution and the 127 vertical levels to achieve the results you're looking at?
How much? What?
Well, how dependent are the results on the resolution that the model has in vertical and horizontal?
Oh, yeah, I think that would depend because if you don't have with 5 kilometers, then we are resolving quite some eddies.
Mm-hmm.
So in the sense, the surface current has also somewhat his own dynamics, as we saw from the case studies. That but if you have coarser resolution, then you will resolve less eddies. And so I will say, if you, in the simple word, the ocean will become more if you have lower resolution, then they will respond more to the atmosphere directly. But if you have increasingly higher resolution, you resolve more eddies and also more sub-mesoscale, also partially. Then the things getting complicated. You can easily get the situation that the ocean does not really directly respond to the atmosphere, because the internal dynamics is so strong that determines the current structure. But we didn't try.
So you don't have some magical cutoff where the dynamics transition.
No.
Oh, that's really interesting.
So may I just add these 2 recent paper I noted, which give you also some lower number, the input. We have to input something like 0.28, 0.23 or whatever, depending on season. And they have also about 0.2 terawatt. And those are also high resolution ocean models. These are, one is MIT GCM 48th degree, and the other is also high resolution, HiCon, I believe. And so these are results with kind of eddy resolving or
Mhm.
strongly eddy resolving model. I guess if you have
Yeah.
coarse resolution, you will get different numbers.
Yeah, it's nice to see the convergence. So, and I don't know if there are other questions, but if I can ask one more. At the beginning, you showed the maps of ERA5 variance or standard deviation and the model standard deviation. And there were really large scale agreements, but there were patches of difference. And I just wondered, is that a function of the short duration of the simulation that you're looking at, or are there actual real differences in those that?
I think that's hard to tell. That's
Mhm.
just 40 days.
Right.
And we choose the same period,
Mhm.
and it's really hard to tell.
Mhm. Right. So it would take
Yeah.
more diagnosis to decide if that was
Yeah, I guess so.
a
Yeah.
statistical difference or not.
Mm.
Really interesting. Are there any other questions before we finish up? I know people have other things they have to get done today. But if not, thank you very much. That's a really great seminar and really interesting.
It's my pleasure.
We'll stop recording.